Thank you, Jerry. And once again, I'd like to thank NewEra Software for sponsoring this series of crypto discussions on the V2R1 Exchange. As you may be aware, we started in January with an introduction to crypto. And then in February and March, we covered the crypto hardware technology that's available on System Z, covering the clear key hardware, the CP Assist for cryptographic function in February, and the PCI cards, the Crypto Express cards in March. And then in April, we started what was supposed to be a two-part session on ICSF. However, due to some technical difficulties with the webcast in April, and just because I tend to be naturally long-winded, we've extended that to be a three-part session. So this June session will be part 3 on ICSF. So with that, I want to turn to slide 2 and point out that if you didn't realize it, I left IBM. I retired from IBM in April of 2014. Gone into business for myself with the company Mainframe Crypto, hoping to do some consulting, helping customers with implementing and supporting the crypto technology on System Z. Now, much of the material we're going to cover today is about the technology, so you might recognize some of the slides. It's based on the work that I've been doing for the past 10 years with IBM. Let's go to slide 3. One of the advantages of not being with IBM is I can cover some of the other technology that's out there now as well. And specifically today, we're going to get a chance to look at the SAF protection that's available for the crypto environment. And with that, I'll be able to cover some of the CA ACF2 and CA top secret products as well. And I'd like to thank Carla Flores from CA for assisting with including those slides. Skipping to slide 4. Again, in April, we covered what is ICSF. We talked about the key repositories and how ICSF relies on verification patterns to provide integrity for the key material that's stored in the key stores. And then we started into a discussion of getting ICSF up and running, the 10 steps that are documented in the system ICSF System Programmer's Guide. In May, we continued with those steps, finishing them up, and then covered some of the other ICSF topics as well. We looked at the panel interface and what you can do. We looked at the health checks that are becoming available with ICSF, as well as the SMF data that's generated and how you can look at some of that material. So this month, we're going to turn our attention to more of the application side of ICSF. We're going to spend some time talking about keys and control vectors and tokens, and then we'll look at the APIs that are available. And then finally, we'll look at some of the security that you can package around your crypto environment. And so that's what we're going to cover today. Let's skip forward to slide 8. This is a slide that we saw back in April, kind of a general introduction to ICSF. What we're going to be focusing on today are the APIs. Over on the right, you can have your own locally written applications, code that you've developed. You can have products, whether they be IBM products or OEM products, that call the APIs, that implement the APIs within the product. And you can also have components like System SSL or PKI services that leverage the APIs. Those all get handed over to ICSF. The first thing he does is some SAF checking, and then he handles the routing of the APIs to the appropriate hardware. So if you invoke a clear key API, ICSF is going to route that to the clear key hardware, the CPAC-F hardware. If you invoke a secure key API, ICSF is going to route that to the Crypto Express cards, and he's in charge of figuring out which card should get the work based on the amount of workload that's spread across the available cards. And as we get farther along, we'll see that there are a number of other APIs, not just tied to the hardware, but that's what we're going to be focusing on today is the application side of ICSF. So with that, we're going to slip way down into the deck, all the way down to slide 46 to pick up where we left off from last month. Now, there are a number of key types that are available. One of the things that ICSF does, well, let me back up. We're going to see on the next slides that ICSF provides implements some variants or control vectors to make a key unique for a purpose. So therefore, there are a host of different key types, starting with the typically what you'd think of when you think of encryption, the data encrypting keys for actually encrypting data. These are the keys that you would use to encipher your DB2 rows, or if you have a record in a file that you want to encrypt within the application, you'd invoke the API and pass the appropriate encipher key to encrypt the data. Excuse me. Alternatively, you might have a little bit farther down your MAC and MAC-VAR keys or your MAC generation keys. Those are associated and only used with message authentication codes. So there's some isolation in the key material. Back up at the top, and there's a typo on that slide. That should be the second bullet, or the second key type there should be clear DES and then clear AES, or CLR DES and CLR AES. Those are clear keys associated with the DES algorithm or the AES algorithm. As you might remember, DES can use a 56-bit, 128-bit, or 192-bit key, whereas AES can use a 128, 192, or a 256-bit length key. So you would define a key of the particular type and store that in your key store, and then pass that key to the appropriate API to perform the encryption operation on your data. The other keys in that list, cipher, data, AES data, decipher, and encipher, those are all secure keys. Now, the ICSF Application Programmer's Guide isn't really very clear in all cases about what APIs are using clear key and which are using secure key. So you generally have to read down through the description, or maybe even look at some of the parameters to know what keys are available, or what keys are supported by a particular API. One of the other things that you'll notice as we go through today is that way back when DES was first implemented, certain key types and certain APIs were implemented. Then as the technology grew, as new function became available, as new algorithms like AES became available, the APIs had to be extended, or in some cases we had to come out with all new APIs to support the new functionality. Similarly with the key types, way back you only had cipher keys. You didn't have clear AES keys or clear DES keys. You also had data keys. Those were the secure keys that were available early. They were DES only types of keys. So the cipher key that's referenced there is specific to a single or double length DES key. The data key was originally a DES key as well. AES data was implemented to provide support for secure AES algorithms. The next bullet there, importer and exporter keys. Importer and exporter keys are used to share key materials securely with a partner. Now, the idea here is, let's say that you have, and let's think back in the early days of crypto, maybe when we didn't have all of the functionality that we have today. If you wanted to share data with a partner on a regular basis, maybe you cut a tape every day that you mailed some information to a partner, and you want it to encrypt that data, well, what you would have to do is on Monday when you create the tape, you might generate a key and use a key to encrypt that data, and then you'd have to call your partner or somehow send to them by another channel, here's the key that I used to encrypt the data today. And then on Tuesday, you would have to do the same thing. You're going to encrypt new data, new file to send them, new key material to protect it. You would have to call them or send them the key for Tuesday. Well, a better way to do that was to provide key encrypting keys. And the idea would be that at the beginning of the month, you would call your partner and say, hey, I'm going to keep sending you data every day, and every day I'm going to encrypt the data with a different key. But what I'm going to do is for the month of June, I'm going to encrypt the data key with another key called an exporter importer key, say ABCD. So on Monday, when I encrypt my data, I'm going to generate a random number. I'm going to use that to encrypt the data. But I'm also going to encrypt that random number with ABCD and stick that ciphertext at the beginning of the tape. My partner then knows when he receives the tape, he'll pull that ciphertext off, he'll decrypt it using ABCD, and then use that clear text key value to decrypt the data. And so he can read the data that I send him. And periodically, maybe on a monthly or even a weekly basis, I would change that exporter importer key that protects the actual data. So that's a specific key type that you can define in the ICSF environment. And again, we'll see a little bit later that if you define a key as an exporter key, that's all it can be used as to export key material. You can't use that exporter value to encrypt data. Data translation, the CipherXI, CipherXL, CipherXO, those are actually fairly new. They're associated with the new Ciphertext Translate 2 API that was reintroduced with the Crypto Express 4S. If you remember, we talked about that in April. Ciphertext Translate gives you the ability to take encrypted data and decrypt it from underneath one key and re-encrypt it underneath a new key, all within one operation that's handled inside the Crypto Express card. And the CipherXI key is the input key or the key that is protecting the input data. The CipherXO is the key that will be used to re-encrypt the data under a new key. The CipherXL is another variation on that, but those keys are specific to the Ciphertext Translate API. Again, the MAC and the MAC generation keys are associated with message authentication codes. HMAC and HMAC var are associated with the new variable length HMAC codes. The standards were enhanced with HCR 7780 to support new variable length message authentication code keys, and the APIs that use those variable length keys require HMAC and HMAC var keys to be passed to them. PIN keys are associated with protecting PIN data, the PIN values that are associated with ATM credit card processing. IPIN Inc. and OPIN Inc. are the input and the output PIN keys for securing the data. The PIN generation and PIN verify is for validating those PIN values. There's a number of other key types as well, things like diversified keys. And the idea with the diversified key is you create an initial seed value that is input to a transaction, and that transaction will then use that seed and calculate a related key from the original seed value. That gives you the ability to, maybe like in a CICS environment where you've got hundreds or thousands of transactions, they can use one common key as a starting point, but then each transaction will have a unique key to protect the data within that unique transaction. So there's lots of key types that are supported by ICSF, and again, we're going to see that they're isolated on the next couple slides. Let's go to slide 47. So when we store a key in our repository, down there at the bottom, we're going to store our operational keys. A data key would be used to encrypt some data, whether it's in a DB2 record or in a sequential file or wherever. A data key is going to protect the data. Stored in the repository, if that's a secure key, that data key is going to be encrypted under the master key, which is up there at the top of the pyramid. We talked about the 5 different master keys that are available when we talked about the Crypto Express cards. Those keys are used to protect our operational keys. Then also in the repository, we can store those key encrypting keys, those importer-exporter keys. They can be maintained in the repository as well, and they will also be encrypted under the appropriate master keys. Let's go to slide 48. Now, ICSF uses something called a control vector to make a key unique for a function. The DES algorithm actually describes something similar called a variant. A variant performs the same function of making a key unique for a purpose. Variants typically are 1 byte in length, and some of the other competitive crypto products use variants. ICSF extends a variant. The control vector is actually the same length as the key. So if you have a single length key, your vector is going to be 8 bytes long. If you have a double length key, your control vector is going to be 16 bytes long. And basically what the control vector is just some bit settings that get XOR'd into the key and effectively make the key unique for a specific purpose. It turns out that there are some attacks that can be mounted by using a key for other than its intended value. So if I have a PIN-gen key, a key that's associated with ATM PIN processing, if I know what that key value, or if I have that key value, I can use it in another operation, like a data operation, just to encrypt data. And from the results of that operation, I can glean some information about the original PIN value. So to make a key unique, so to make sure that a PIN key can only be used for PIN operations, we apply these bit settings to the key, and that effectively makes it unique. And the way the process works is when we're going to encrypt our data key for storage in the key store, first we're going to XOR the control vector to the master key. So we're effectively tweaking the master key to set it for a specific function, and then we use that to encrypt the data key or the operational key that gets stored in the key store. It makes the key unique to a specific function. You can't use a PIN-gen key in a ciphertext operation within ICSF. You'll get different results because of the application of the control vector. Let me pause and take a drink. And we're going to go to slide 49. Excuse me. There's 3 ways to load keys in the ICSF world. There are a number of APIs, and we're going to see many of these a little bit later on today. These keys give you these APIs give you the ability to generate and manage keys. So there's a keygen API, which will go out and generate a random number and then create the token that can be stored into the key store to make that key available for use by other APIs later on. There are APIs for importing and exporting keys so that you can exchange keys with your partner, and these APIs will all handle those control vectors appropriately. If you're communicating with a partner that does not use IBM CCA architecture, then you're going to have to strip off those control vectors so that the partner can understand them. The partner is probably going to have to apply their control variant, whatever variant the products that they use implement, but that'll be the customer's or the partner's responsibility to do that. The other way to create keys is their second way is using the Key Generation Utility Program, or KGUP. Basically, ICSF provides a batch utility. You can code up the JCL and the control statements that will generate key material. So down there toward the bottom of the page, KGUP uses as input. That first line is a comment, the data encryption tool AppX key for tables. The control statement itself, this one is adding a data key for encrypting data. It's going to be associated with the AES algorithm, and it's a full 32 bytes, 256 bits long. And this particular key is going to have the label assigned of greg.db2tool.appx.d140411, and that's just coding that I added so that I know that this key was created on April 11th of 2014. Now, ICSF also provides a panel interface, basically a screen where you can fill in the blanks. And on the next slide, we're going to look at that panel interface and specifically the parameters that were used to generate that control statement. And then the last way to generate operational keys is via the Trusted Key Entry Workstation. We talked about the TKE when we talked about the hardware in March. The TKE is basically a standalone Intel box with a Crypto Express card installed. You can generate key material inside the tamper-resistant boundary of the card and then securely push that up to the host system. Let's look at the KGUP panel on slide 50. So this is the panel when it's first presented. It's blank. I filled it in with the information in red. So up at the top, we tell it whether we're going to add a brand new key, or maybe we're going to update or change an existing key, or you can delete a key using the panels. Then tell it what algorithm. This is going to be an AES as opposed to a DES key. And then the label parameter says, all right, this is the label that we're going to associate with that key. That label is how it's referenced. You'll point to the label in the API. The label is also used to provide SAF security for the key material. So just like you can set up a dataset name profile, you could set up a CSF keys profile specifically for greg.db2tool.appx.d140411. Or you could create a more generic profile, just greg.db2tool.splat, which says anything that starts with greg.db2tool is going to be protected by this particular SAF profile. There's a length of key down toward the bottom. I told it to create a 32-byte or 256-bit AES key. And then the comment line, as we saw on the previous slide, that gets put into the control statements. The comment does not actually get stored into the key store as part of the key record. Now, a couple other of the parameters on here. There's key values. If you wanted to generate a clear key, you could actually hard code the values of the key into that field there, and that's the key material that would be created. Now, remember last month we talked about special secure mode, and you have to have special secure mode set to yes to be able to enable ICSF to process keys in the clear, as this is certainly going to pass through your TSO address space. You also have the capability of generating something called group labels. So you could create 100 keys or 1,000 keys with a common label and then a sequential number that gets tagged on the end. So there's lots of capabilities here in terms of being able to manage keys. But it is a batch process. This panel would generate the JCL and the control statements that you would in turn have to run to actually generate and put the key material into the key store. Let's go to slide 51. ICSF has two different key formats, well, first, the key tokens are how keys are stored or structured within ICSF. When you create a key, you actually build this thing called a key token. That key token is part of the record that gets put into the key store. So the record in the key store has a particular format. It's got some control information about the record, when it was created, that sort of thing. In addition, within that key record is this thing called a key token, which actually contains the key material as well as flags and bit settings that indicate how the key can be used. So an external key or an internal key, the key material is encrypted under the master key. ICSF, when it's using keys internally, keeps track of them in that encrypted format. Alternatively, you see there are a couple of external keys. Those are keys that are no longer encrypted under the master key. And the idea is you might be going to send this to a partner. So you've got to get the key, decrypt it from underneath the master key, and then you're going to turn, and that's external format, and then you're going to turn around and encrypt it under an exporter key or under an RSA key to be able to ship that or send that securely to a partner. These key tokens are all documented in the ICSF Systems Programmer's Guide. The layout for all of these is in there. So if you have access to the key store, you can pull the key token out of the record and look at the flag settings, look at the bit settings to see exactly how the key can be used. Let's go to slide 52. We're going to turn our attention now to the APIs. Okay, so we've talked about the keys. Now we're going to talk about the APIs that will likely point to those keys. The first thing to keep in mind is that the APIs are going to have some dependencies on the hardware that's available. In terms of the crypto cards, some APIs will work on the Crypto Express 4S, but they won't work on the Crypto Express 3 or the Crypto Express 2. Other APIs will work on the Crypto Express 3 and maybe not the Crypto Express 2. You can also have a dependency on the server. So Crypto Express 3s were supported on the Z10, the Z196, and the ZEC12. However, each generation added new crypto functionality. So if you had a Crypto Express 3, the function might be available on the Z10, but not the Z196 and the ZEC12. So the APIs are documented in the ICSF Application Programmer's Guide. In that documentation for each API, there's a section called Usage Notes. And the usage notes summarizes what hardware is required for the specific API. So that's something you're going to need to look at as you start writing to the APIs. What hardware is required? Because if you implement an API that requires the Crypto Express 4S to run, then you're going to need to have a Crypto Express 4S available. Otherwise, ICSF is going to give you back some error messages or return codes and reason codes that say, I don't have this hardware that you need to perform this specific function. So that's something that you have to check as you're writing to the APIs. Now, the APIs are supported by COBOL P01C as well as a native assembler code. They're also available via Rex. So if you're trying to understand how an API works, writing some simple Rex code to invoke the API and then maybe looking at the output, that's a really good way to get to learn how the APIs work, to understand exactly what functionality and what each is doing under the covers for you. The APIs can be implemented in problem or supervisor state. You can run them in task or SRV mode, although there may be some restrictions within the specific APIs. As of HCR 77able0, all of the APIs provide 64-bit support. That was not true in prior versions of ICSF. There's a number of there's alternate entry points available for some of the APIs so that you can access data in data spaces as well as in the directly in the address space, the program address space. Slide 53 provides kind of a summary of the naming conventions for the APIs. There's the CSN prefix, or CSNB prefix indicates that it's a 31-bit support. CSNE is 64-bit support. The PKCS11 APIs all start with CSFP as opposed to just CSF for the more utility type APIs. Now, there's also some suffixes that are provided as well with if there's a, let me pause and regroup here. Some of the APIs were written way back in the dark ages of crypto support. As new function has come out, if we could, ICSF would try to extend the existing APIs to support the new functionality. However, that's not always possible, so there had to be a new API that was very similar to the existing one, but that supported new capabilities, new technologies. So those new APIs would have a suffix of 2. So an example might be the CSNB KRW and KRW2, Key Record Write API. The original KRW API supported the fixed length CKDS that was around for years and years. With HCR 7780, we introduced a variable length CKDS to support those variable length HMACs. Now, to write to the variable length, to write variable length records into the CKDS, you need to move to KRW2. It provides a lot of the same functionality as KRW, but it supports that new format. Similarly, the CSF IQF, the query facility, there's a CSF IQF and there's an IQF2. They provide similar function, but we'll see when we talk about the APIs a little bit later on, IQF is a little bit different in what information it returns. Let's go on to slide 4. So the next several pages are going to be a summary of the APIs that are available in ICSF. With HCR 7781, we're up over 130 different APIs that are available. The vast majority of those are associated with symmetric key management. This page is full of APIs that are associated with managing symmetric keys. The next page continues the list. So there's APIs like key generate. The key generate API will generate a symmetric key for you. It will go out, it will go to the Crypto Express card to get a random number that can be used as a key, and then based on parameters that you provide, it might make that an AES key, or it might make it a triple DES key, depending on what your requirements are. So that API you can invoke and generate key material. Key import and export, those would be used to, if you're going to export that key to a partner, it will put the key in a format that can be exported. Key token build will build the structure that you need to plug that key material in so you can save it eventually in your key store. Key test has to do with checking the integrity of the keys. There's some check values that you can calculate using keys. So you can perform those checks within the application to make sure that you've got the right key material that you're going to need to perform the encipher, decipher operations that you're going to need to do. On slide 55, again, some more symmetric key management APIs. The TR31 keys. TR31 is Technical Report 31. It's associated with one of the ANSI standards. That the ANSI standards talk about specific ways that you have to do things like wrapping key material. The TR31 is one technical explanation or description way to implement the ANSI standard. It's a recommended but not required way that describes, okay, we're going to package it like this, and this to meet the standard. And so ICSF provides some APIs that specifically implement the TR31 technical requirement. So if your organization is subject to or has chosen to implement TR31, there's some specific APIs that will help you do that. Over on the right, there's just a handful of APIs that are actually associated with encrypting and decrypting data. And there they are on the right. So the CSNB, DCO, and ECO, decode and encode, those are old APIs that implemented DES using ECB, or electronic codebook mode. Now, if you remember when we talked about electronic codebook mode, it's not the most secure way to do things. So later, ICSF came out with the CSNB, ENC, and DEC for encipher and decipher. Those implement DES as well, but they do it implementing cipher block chaining to provide a little bit more security. Now, later on, when the AES algorithm came out, the PSI-D and the PSI-E APIs, those provided clear key triple DES encryption. They were extended to also support AES. So those two APIs, PSI-D and PSI-E, support both triple DES and AES encryption using clear key. But ICSF did not extend the encipher and decipher APIs to support AES. There, they implemented new APIs, the SAD and the SAE APIs, to perform AES secure key encryption. So again, this goes back to when ICSF could, they would just extend the existing APIs, but they couldn't always do that. Sometimes they had to develop brand new APIs to implement the new technology, the new function that was available. Let's go to slide 56. Slide 56 covers, on the left, we have APIs associated with data integrity. Those are the hashing APIs for generating hash values, specifically the CSNB OWH, one-way hash. You can pass parameters to the one-way hash that says I want to generate a SHA hash, in which case that work will get handed over to the CPAC-F card. Or you can specify doing an MD5 hash, and if you remember, the CPAC-F hardware, or none of the crypto hardware, supports the MD5 API or MD5 algorithm. So that is implemented in software within ICSF. So if you use MD5, you're not going to get any hardware benefit, you're not going to get any hardware performance. Down at the bottom, well, in the middle, you have the MAC generate and MAC verify. Those are APIs to generate message authentication codes. The hashing with the symmetric key is input. At the top, you have the HMAC generate and verify. So those are the APIs that use those new variable length message authentication code keys that were introduced with HCR 7780. On the right, the financial services APIs, these are pins or APIs associated with generating and verifying PIN values. There's quite a few there. Notice that down toward the bottom, there's some that are specific to Visa. So Visa has come out and said that there's some techniques that we want to use to generate the CVV values associated with the credit card. Those APIs specifically implement those Visa formats. Up toward the top, you have the CVV key combine, kind of more of generic CVVs for other credit card operations. Let's go to slide 57. Some more APIs. The first two are associated with generating and verifying digital signatures, so you can sign messages and say this message really came from me because it's using the signature public-private key that's associated with me. On the bottom on the left, we have APIs that are specific to the PKA operations. So you've got a PKA key generate. This will generate a public-private key pair that you can use. There's APIs to create and build the tokens so you can store those records in the key stores or in the PKDS. Over on the right are the APIs for actually reading and writing to the key stores. So you have key record read. That'll go out and read an existing record in the CKDS. Key record write will write a new record to or write a record to the CKDS. Again, notice that there's several versions there. There's a KRR and a KRR2. Again, the 2 value is associated with the variable length CKDS that was introduced with HTR 7780. There's a different set of record writes and record reads for the PKDS down there toward the bottom. On slide 58, there's a number of utility APIs. These aren't associated with any specific hardware. These APIs, it turns out, can also be invoked even without ICSF being up and running. Well, some of them can be invoked without ICSF up and running, specifically the character nibble conversion and the code conversion APIs. The code conversion API gives you a way to translate hexadecimal data from EBCDIC to ASCII and back. There's a table default table that ICSF uses for that conversion process, but that's a handy thing to have, if you need to do character conversion. It's not really crypto, but it is a function that crypto can use as well. The query algorithm returns information about what algorithms are available and supported in the current environment. Similarly, the query facility gives you information about the hardware that's available. Now, that can be some pretty detailed information, even down to the microcode levels of the Crypto Express cards, which maybe you don't want just anybody to be able to look at that, and you don't want just anybody to be able to invoke this API and see what's implemented in the hardware. So with the latest version of ICSF, HCR 7781, there was a new API introduced, Query Facility 2, which provides a much, simpler or higher level view of the crypto environment. And really the difference is Query Facility 2 provides less information, so there is no SAF protection around QF2. The original CSF IQF, there is SAF protection, so you can configure in your environment so not just anybody can implement that API, but the IQF2 doesn't have that SAF protection, so anybody can execute it. On the bottom left, Trusted Key Entry Workstation Interfaces. This is the API that provides communication with the TKE. And then over on the right are the PKCS11 APIs. Now, if you remember way back in the intro, we talked about IBM implemented the Common Cryptographic Architecture, but then several generations back, ICSF introduced for PKCS11 as defined by the RSA. Now, PKCS11 can do symmetric encryption using DES and triple DES and AES, and it can do public-private key encryption as well. These APIs implement all of that support, but they do it in a way that maps to the PKCS11 architecture, the PKCS11 structures, as opposed to implementing the CCA infrastructure. So you have some of the same capabilities, it's just the infrastructure that you're using, the architecture that you're using is going to be different when you use PKCS11. Let's turn to slide 59. So those are the APIs. All of the APIs work similarly in that you invoke the APIs and then you pass a string of parameters. All APIs have the same first 4 parameters: return code, reason code, exit data length, and exit data. The return code, ICSF will give you a 0, 4, 8, 12, or 16. 0 is everything went wonderfully. 16 is there was a disaster. And if it's 4, 8, and 12, then you fall somewhere in between those extremes, just like you do with conventional return codes from a batch job. The reason code provides a little bit more detail about the specific error. So these are all documented in the ICSF manuals. You go look up the particular return code, and then you look at the reason code within that to determine exactly what went wrong. So, it's not uncommon to see somebody implement an API that requires a Crypto Express card but not have a Crypto Express card installed. And you'll get a particular return code and reason code to indicate that. The exit data length and the exit data, if you have an exit associated with the API, you can pass data to that exit. Whatever your exit is going to be doing, you might expect certain data to get passed to it. This is where you would specify it. Now, after those first four, the rest of the parameters are positional and they're unique to the API. So the APIs that are the parms that you pass to a CSNB in-cipher operation are going to be very different, and the number of parms you're going to pass is going to be very different from a key generation operation. They're performing very different functions, so the parameters are going to be very different. Again, there could be a few or many parameters. They are positional, so you must code all of them with the proper positioning. And then we're going to see in a minute, one of the parameters that you pass is something that's common to a lot of the APIs, is a parameter called the rule array. And the rule array is just a string of 8-byte keywords that the API expects to describe the environment. So we're going to see in a minute that one of the rule arrays for the encipher and decipher is expecting a parameter to tell it what type of cipher blocks chaining to do. So this rule array, again, the number of values in the rule array is going to depend on the API. You need to tell it how many there are, and then you need to fill in the various parameters you want to use. 8 bytes, each keyword is 8 bytes, and if they're shorter than 8 bytes, they've got to be padded with blanks, just left justified. So let's go to slide 60 and look at an example. So this is the encipher decipher API. This is the API that you would use to encrypt data. You see the first four the first four parms, and both of them are that return code, reason code, exit data length, and exit data. By the way, I should have mentioned when I talked about those, it's up to your application to query that return code, reason code. And if it's other than a return code 0, reason code 0, you might want to externalize that result and let the application know, hey, there was a warning message here that there's something that maybe somebody should investigate. The next parameter for both APIs is the key identifier. That's a pointer to the key that is going to be used to do the encipher and decipher. The text length tells it how long the data is that's going to be encrypted or decrypted. Clear text on the encipher operation is going to be the text that you're going to encrypt. For the decipher operation, it's where the decrypted information is going to be put when the API is finished. Initialization vector is associated with cipher block chaining. That's the IV, or initialization vector, to use for the first block of data. If you remember when we talked about cipher block chaining, each operation impacts the next operation. And the initialization vector is just the first input. What should impact that, what data should impact that first operation. Then again, the next parameter is the rule array count, how long the rule array is, followed by the rule array. And we'll look at the rule array on the next slide. The next parameter for the CSNB in cipher is the pad character. Now, if you're encrypting, if you're doing DES encryption, DES works on 8-byte blocks, And if you pass it clear text of 15 bytes, then it needs to pad that to make it 16 bytes so the DES operation will work. So in the pad character, you specify, pad it with blanks or binary zeros or whatever you want to put in there. And the encipher operation will fill the block out to make it a multiple of 8. Notice that you don't specify the pad character in the decipher operation, because when the encryption or the decryption is done, your clear text is going to have that pad character at the end, and the API doesn't really need to know what it is going in. The chaining vector is a work area for passing the chaining information when you're doing cipher block chaining. And then ciphertext at the bottom for the encipher operation. That's where the encrypted data is going to be put when the API is done. For the decipher operation, the ciphertext is the input, and that's what's going to get decrypted. So let's look closer at the rule array on slide 60 or on slide 61. So for the encipher and decipher operation, there are 3 possible values in the rule array. The first one is required. That tells the API what type of chaining it's going to do. Is it going to do cipher block chaining, or is it going to use one of the older techniques like CUSP or IPS? CUSP would be consistent with using the cryptographic unit service program that we talked a little bit about last month with compatibility mode. Excuse me. The second parameter is optional. The default is initial. It tells ICSF, hey, when you invoke this API, this is a continuation. We're looping through some data, and I want to pass an initialization vector from a previous operation. In that case, you'd specify continue here. If you specify initial, then it will use that initialization vector that you pass to the API. And then the last rule array parameter is DES or token. That has to do with manipulating some of the CCA bits within the environment. If you need to do some things that outside of CCA, you might use that token value to manipulate those bits and let it override the bit settings. I'm going to take a drink as we go to slide 62. I didn't mention it before, but I should have. When you specify the key identifier, you're telling the API what key to use. But there's actually a couple different ways that you can pass the key information to the API. The first way is via a key label. So if you think back to that KGUP example where I created a key that started with greg.db2tool.appx, the key label could actually point to that label, a 64-byte character string, right padded, that references a key that is in the key store, in the CKDS. So the key identifier would specify key identifier equal greg.appx. Whatever. Alternatively, you can point to the key token. So remember when we talked about key tokens, when the record's stored in the CKDS, the token is embedded in the record. So what you could do is you could do a key record read, bring the record in, and then pull the token out of the key record and directly pass that token to the API. It's a 64-byte structure, and there's bit settings in there that indicate how the key can be used and all. But by doing that, you can get a performance benefit. If you are looping, encrypting or decrypting lots of records, and you use the key label operation, every time you loop through, you're going to go get that record out of the data space and then use that to perform the encryption operation. If, on the other hand, you use the key token, what you could do outside the loop is pull the record in, pull the key token out, and then loop pointing to the key token key token, and you by doing that, you are not going through the overhead of doing the get the key out of the data space or out of the key store. So that's a technique you can use to provide some improved performance. Then the third option there is, instead of pointing to the key label or instead of pointing to a key token, you can just point to the actual key value. So if your key value is ABCD, you can point to ABCD, that string, and that will get passed to the API as well. Now, ICSF will use some techniques. He'll look at, is this a 64-byte padded character string? And he'll figure out okay, I got to go to the key store. Or he'll look at the bit settings of the token and say, is this a token structure that I expect? Okay, yes, it is. I'll use that. And then if it's neither of those, then he'll treat it as an actual key. Now, the thing to keep in mind with using the actual key material, that is, by definition, clear key. So if somebody can take a dump of your address space, they could see your key material if you're using that technique. Let's go to slide 60. I'm going to turn the page a little bit here and talk about SAF security. We've talked about this as we went along. There's three types of resources you can protect within the ICSF environment. You've got the CSF keys class, so you can protect using the key label. You can protect some of the APIs. Not all of the APIs have this capability, but many of the APIs and some of the ISPF panels can be protected by specifying the CSF serve class. And then lastly, we have KGUP. You can restrict who can invoke the KGUP utility. You probably don't want just anybody being able to generate keys or delete keys, so you probably want to restrict access. The next couple slides talk about the various security environments. So from a RACF perspective, you first must do the RDefine for the CSF keys class, and then which specific class, the label that you're going to protect. You're probably going to set these up with a UAC of none, and then individually permit individual users, user IDs, or groups to have read access to that key material so that they in fact can pull in the keys. It works similarly for CSF serve. You're going to protect the specific service. So you might protect the CSN B KGN, or CSF KGN. So you're going to give the key generate API is going to have a UAC of none. Not just anybody can use it. And then your key officers, or the group of your key officers, the group that's defined with the key officers assigned to it, they would likely have read access to be able to implement that KGN API. And then it works the same way for the KGUP. You permit CSF KGUP, and that's also in the CSF serve class. On slide 65, these are the commands that you would use in the top secret environment. And top secret being very similar to RACF, you're going to see this permit, and then you permit the specific user ID or profile to the specific CSF keys label. Again, you're giving them read access. And then on slide 66, the same information for ACF2. It's been a long time since I've done work with ACF2. And a little bit more involved in setting the resource and then performing the compile. But if you're familiar with ACF2, this will all be second nature to you. But you do have the capability to protect the keys as well as the service classes within ICSF. And then I think the last slide that we want to cover are some of the facility support, the key store policies that have been implemented in the last couple versions of ICSF. They use the xFacility class in RACF. A couple examples of things you can do. I'm not getting into a lot of detail here, but things like duplicate key token checking. Vanilla ICSF, you can create a key, let's say a key with a label of key 1 that has a key value of ABCD. And then somebody else could come along a little bit later and create another key, key 2, with a value of ABCD. Auditors don't, and security folks don't like duplicate keys because key 1 might have the proper security wrapped around it so that only production can use that key. But key 2, which has the same value, maybe is authorized to a group of testers. So if those testers could somehow get access to the data that was enciphered using key 1, they could use their key 2 to decipher the data fairly easily. So auditors don't like duplicate keys. ICSF has implemented this duplicate key token checking. If you turn it on, ICSF will look and see if there's already a key in the key store with that particular value. And if you remember, we talked about the fact that when you create a key, ICSF will create a hash of the key value and store that with the record. And that's how he validates or looks for duplicate keys. If you create a key of ABCD, he'll create a hash that represents ABCD, and then he'll scan the existing CKDS to see if there's already a record in there with that same hash value. If duplicate key token checking is turned on, it won't let you put that second key into the key store. So it's optional. If you implement this policy, you can provide that kind of checking. Key token or default key label checking says if you pass a key identifier, remember we talked about key identifier, you can point to the label or you can point to the token. Default key label checking says if somebody passes in an API the token instead of the key label, well, he doesn't have the label, so he can't check for RACF authority to use that key. But when you turn on default key label checking, ICSF says, there's no label associated with this key. I'm going to use a generic label and go look for a RACF profile to see if they can use that key material. Key token authorization checking works a little bit similarly in that if you use a token, if you pass a token to the API instead of a label, ICSF will calculate the hash of that key value in the token, and then it will scan the CKDS or the PKDS looking for a record with a label that has the same hash value. And if it finds one, then it will use that key label to perform the authorization checking to see if you're authorized to use that key material. So what that policy is doing is extending some of the key checking, key authorization checking that goes on to make sure that you are in fact authorized to use the key via the key label. So it's just some additional security for your key material. You can read about the key store policies in the ICSF documentation. Symmetric key label export control. Even if you're authorized to use a key, that doesn't mean you should be authorized to export that key and maybe send it to a partner who's going to steal some data. So there's some additional checking that goes on to make sure, well, yeah, even though you're authorized to use it, we're going to check and see if you're authorized to export that specific key material. So I think that pretty much wraps up everything. On slide 68, I've got references to the ICSF publications. Be aware that when we went to ZOS 2.1, the manual numbers all changed. So all of the manual numbers you had memorized, they've all changed. So you need to look at the appropriate manual for your version of ICSF. With that, I'm going to turn the session back over to Jerry and let him open up things for questions. Thanks very much.